Okay, I'm back. Sorry about that. Right, so I have no idea what just happened. My computer just turned itself off and then turned itself back on again. No clue what was going on. The intro song is probably something from Josh Woodward. Let's go over here and do Josh Woodward. I don't exactly know what it is. It's kind of on random, so I have no idea what the song was. But it's one of these guys. He's a good Creative Commons intro artist. I'm a big fan of his work. So I tend to use it for all my videos and stuff like that. So it's one of these. I have no idea which one it was because I can't see which one was playing. So I do apologize for that mishap. I'm not exactly sure what happened. My computer has been nice for the past week since I got a new... Oh, has it been a week? It's been like 4 days since I put in a new motherboard. So actually, give me just a second. Let me check something. Okay, it's probably fine. Yeah, okay. Let me check my sensors as well. Okay, sorry, I'm... Sensors... I mean, it's only 42. That's kind of hot, is it? It's not that hot. I mean, it should be fine. Okay, I have no idea what happened there, and I'm really sorry about that. But we can go ahead and hop back into it wherever we left off. So let's open up Xernal PP. Actually, oh my god, I'm all over the place. I'm all over the place. I'm sorry. This is super unprofessional. Wow. How am I ever going to be a professional Twitch streamer if I can't even keep my computer on? Let's Quiltify. Me. Okay. Move this up here. I don't know, move it over here a bit. Move this down. Good. So we're basically where we are just a second ago. Perfect. Okay. We'll zoom in a bit. Yeah, perfect. Okay. Now let's open up Xernal PP and let's answer some of Meowcat's questions. I saw it. I just wasn't able to answer it because of everything else. Okay, so we were just talking about color quantization. You won't need to worry when it starts hitting 100 Celsius. Right. Okay, so Meowcat asked a few questions. Could you please ask those questions again? Because I cannot see... I cannot see the questions anymore, and I don't know where they were, so I'm gonna have to scroll up a bit. But yeah, so we were talking about color quantization. So let's just do that one more time. So here we have some sort of giant box. And in principle, it's a 3-dimensional box. But we are going to just say it's a 2-dimensional box where this axis is the red axis and this axis is, we'll say, the blue axis or something like that. Then what we have is a whole bunch of points in our 2-dimensional space that are somewhat red and somewhat blue. And the idea is we have some sort of giant box at the start, which covers all the particles, right? As a giant box. And then it has 4 children, box 1, 2, 3, and 4, right? And so then this box is split up into 4 more children, 1, 2, 3, 4, some of which are empty, some are not. This one's split up again, so 1, 2, 3, 4. This one's split up again, this one's split up again. So this one's split up 1, 2, 3, 4, and then we have another one, 1, 2, 3, 4, and then this one's split up here, 1, 2, 3, 4. So in this way we have a tree, not necessarily an n-ary tree, but a tree nonetheless, which corresponds to essentially every single particle in the simulation, every single color in the simulation, or in the color quantized image, the image that we're trying to color quantize. I don't know how to put that, but the point is, this essentially turns into a tree traversal. Tree traversal, a simple tree traversal, where we're just trying to find the n biggest boxes, and once we find the n biggest boxes, we can then figure out what the colors are that we use in the end. I'm sorry, I'm all over the place today. It's been a day. Less than 60 degrees Celsius should be perfect. It can go to 100 Celsius, but it reduces lifetime. Yeah, so I think yeah, I don't know. My CPU and motherboard just died the other day, so I'm kind of really... I'm worried that my computer's dying again. I don't know. Okay, so I've replaced the CPU and motherboard. I've replaced the hard drives. I've replaced the power supply. So the only thing that's still there from my old computer is the RAM and the GPU, right? So, like, there's no way the computer would have rebooted because of, like, RAM or GPU issues, right? The Ryzen 3700X, and I don't remember the CPU. I don't remember the motherboard exactly. RAM? You're saying that RAM can turn off the computer? RAM is easy for it to reboot, so maybe the RAM is also going bad. Oh man, I mean, I've had the computer for 6 years, right? So at this stage, you probably expect some of the parts to go bad. 1 second, I got a notification I have to check from work. Give me just a second. 6 notifications from work actually. Okay, good. It's okay. I don't have to respond directly right now. Okay. If you later go to replace the GPU and RAM too, is it a new computer then, or is it the same as the original? I mean, that's a good question, right? Like, you as a human shed like a cell every minute or something. I'm making up. You, in 6 years, apparently replace almost every cell in your body or something like this. So, are you still the same person, or are you a different person? I don't know. It could be software based as well. Could be. Also, I do shut down my computer with the phrase sudo power off. That's what I do to shut down my computer. So it could have been that I accidentally somehow ran the sudo power off command in another terminal. I don't know how that could have happened, but it could have happened because it's in my history somewhere. I'm just not going to worry about it unless it happens like regularly, which I don't think it'll happen regularly. But if it starts happening more, then we have to deal with it more. I've heard this too. All cells are replaced in 6 years, but I wonder how this works for bones. Yeah, also brains, right? Like, are brains replaced? So unfortunately, I don't think I got to Meowcat's questions because I don't see them in chat anymore. But hopefully this helps out anyone who might be questioning what we're doing exactly. Okay, so let's get started on the next stream. So we're gonna go here, and we are just gonna make this a little smaller. And then we're going to cd into projects, Quiltify. And go over here, cd projects, Quiltify. Okay. Also, Stealthar, thank you so much for following. Really appreciate it. When your brain cells die. Yeah, so also, I probably sent out 2 notifications because my stream did officially close and then open again. So it wasn't like I was trolling for more people. That was just a genuine accident, and it happened to coincide with about the time that I would normally change stream topics anyway. Okay, so let's go here, vi source, and then quantize. Okay, and we've got a bunch of to-dos up here, at the top. We have the quantization may fail if no colors are available for a box. Some boxes return negative mean colors, which isn't good. All colors are the same in the color set, which isn't good. We need to take the top n most populated boxes, which is what I just described earlier. That's not what we're doing here for a simple case. And we might want to switch to an Hsv color space instead of using RGB. So that's where we're at. So then you are the brain, you are the same person, it's just the meat shield that is continuously replaced. Yeah, right, Simulus is trolling. What am I trolling about? I'm sorry about that. I'm genuinely not trolling, but I don't know. Okay. So let me move down to this Quantize command, and also just for the record, we wrote 130 lines last time. Oh my gosh, I'm sorry, I hit the microphone. We went through a lot of, we got a lot done last time. So let me explain just the Quantize command, and then we'll describe the other functions as we need them. So here we have the image out that we're going to be writing to. We then have some sort of box, which is going to be that octree structure. The big box has little boxes inside of it. And then we have this thing that I called a color set. Now the color set is the quantized colors. It's the set of colors that you'll be using in your final color quantized image. Then you have the function find color set, which should basically find the appropriate color set. And then I have this debug statement println color set. Then I say for I equals 1 to length of image out. So we're just going through every single pixel in image out. We say that the distances, we find the distance of that pixel's color to any color, to every color in the color set. So if there are 8 colors, we then find the change in the color of that pixel to the change in or to any of the colors in the color set, and then we find whatever color that pixel happens to be closest to, and then we set the image out equal to that value. So we find, I'm not doing a good job of describing this. Essentially, we go through every single pixel in the image, we figure out which color in the color set is closest to that pixel, and we use that color for that pixel. That's what we do. This is an old myth. New research shows that you can grow new brain cells. Fair enough. Well, some parts of the brain do get replaced, but other bits don't. Yeah, there's also like big questions as to what happens with like lesions and things like that. I mean, I used to do a lot of neuroscience research, but I haven't done it in a while. Julia double dash project, using revise, and now we're gonna do using Quiltify. Quiltify. Okay, so I am going to create an image, and then after creating the image, I will then show the image. And then after showing the image, we will then show exactly what's going wrong with the color quantization and try to fix it. So we've got a lot to do. We'll get there slowly but surely. I'm hoping that by the end of today's stream, we have a working color quantization. And then throughout the next week, we can finish the rest of the stuff with Quiltify. Now, I have no idea when this is going to turn into a video. I know that the color quantization bit that we're working on now, I do genuinely want to put in the algorithm archive, because it needs to go in the algorithm archive, and we already have a YouTube video available for it. But the question is, when are we actually going to be using the Quiltify function? Well, you'll find out. Haha. We'll use it. I have an idea for a video. It's just kind of floating there, and I don't exactly know how to turn it into a full video. And I'm kind of booked for now, so I don't really know what... I don't really know when I want to turn this into a video, but it will. It will eventually. Okay. So, let's see, we have Quiltify, we used Quiltify, so let's see if I have an image command in here. Image is equal to this, sure. RGB not defined because I need to be using images, and probably image view. Okay, that took no time, image is equal to RGB. Okay, so now if I do imshow of img, we should get an image with some sort of smooth gradient. It's a small image, but an image nonetheless, with some sort of smooth gradient. All right, fine, fair enough. There you go. There's our smooth gradient. It's blue in the upper corner, and then it gets less blue as it goes further out, and then it's red and green, and yellow when red and green combine. Cool. Okay. So what I'm going to do next is I'm going to run quantize on the image, which will return image 2. So image 2 is going to be equal to quantize. Quantize. Probably quiltify.quantize. Quiltify.quantize. And then we're going to do image. And then the number of colors we're going to set to be 8. Okay, so now if we plot. Now if we imshow img2, we're going to get garbage. Yeah, it's pretty bad. All of this over here is apparently negative values. So we've got a lot wrong here. So the first thing that's wrong is that for some reason, we've got a negative in blue over here, and I don't know why exactly. So we're just gonna have to figure this out one step at a time. There's a lot of just stuff that's broken with this code right now. So we're gonna have to do it. So the first thing is when we find the color set and we print out the color set over here, note that the color set has the same colors. So it's 0.505, 0.505, 0.505, negative 1.02. So for some reason, our color set, all of the colors in our color set are the same color, except for this, which is black. So we've got to figure out why our color set isn't the appropriate color set. So that's one thing we have to figure out. And then we need to figure out how to... Yeah, we got a lot of stuff. So let's focus on the color set problem first, as to why all of the colors in our color set are the same. And then from there, we will start attacking other things. So we should be able to just do find color set. How did I do this? So I think what I need to do is change find color set to have be changed color set with an exclamation mark. And then find color set with an exclamation mark. It doesn't matter that much. I just wanted to do it. So then we're going to go over here. We're going to do quantize again. So we get those functions loaded by revise. And then we're just going to mess around, see what we can do. You can get an even smoother gradient if you cube root the color values first. Yeah, I guess so. Okay. Let's see. No method matching find color set. I apparently have some find color set. Here. There. Oh, here it is. We need an exclamation mark there. Try it again. Okay, so that seemed to work. Well, it didn't work, but we got the same result as last time. So let's figure this out. So what does the function find color set do? It says if index is equal to if index 1 is greater than the color number, which basically means if index 1 is greater than the color number, which basically means we have more indices. We've already filled up our color set. We already have all the colors chosen for us. Then we say, I don't know how we have negative amounts of blue. I have no idea. That we've got a bunch of mysteries with this code that we need to solve. So it's gonna be a thing. This is gonna be a bit demanding. So we'll try to figure it out. So what does this currently do? It basically says we need to collect 8 colors, right? So I have some sort of index, which is the color and which we are currently within the color set. So here we say color set of index 1 is equal to box color. So index 1 is going to be an integer. So this is an array of integers. Now I did it as an array of integers so that as you're traversing through the tree, if any element in the tree updates that location in memory, everywhere else on the tree will know that that has been updated, right? So that's one reason I did it that way. Again, you could do some sort of information passing, which would probably be the more correct way to do this. But for the purposes of this particular, kind of quick, dirty, get this thing working, I did it this way. So then we say if the index is greater than or equal to the color number, meaning that you have, well, actually, probably just greater than color number is what we want. That's probably why we had that one color in the color set be all blacks because of this. Okay, so if it's greater than the number of colors that we want to collect, so that is to say we already collected all the colors we need, then we just return. Then we say if box.color is equal to nothing, is not equal to nothing, which basically means there is some value that is associated with that box. Then we say color set of the index 1 is equal to box.color, and then we add 1 to the index. We say we've added something to the color set. And then we go through all the children in the box.children, and we say we find the color set, and we say color set box index color number, right? So it could be an issue with the octree itself. I feel like it might be an issue with the octree. So here we have this divide octree function, which basically says, let's go up here to divide octree. Where do I set the color for this? So we initialize the box here, and the box is set to be, this is the big box that's encompassing all of the other boxes, and it's just set to be the average of all of the colors in the image. So it's just sum of image divided by the length of the image. Okay, so that's the color of the big box. And then we say we don't have any children yet, we'll add them later. And then we say the extents of the box are going from 0 to 1, 0 to 1, and 0 to 1, again in RGB space. Then we divide the octree. So the octree says if the level is greater than the maximum level, that is to say, if we are going too far. So basically, we only want to divide the octree up unto n levels. And so for this, we're just saying if we're greater than that maximum level, we don't have to worry about it. Again, in principle, octrees will have every single pixel have its own box, but we're just doing it in a different way now, and we'll worry about that later. Then we say the children is going to be color box of nothing, so that means we have no color associated with it, and again, they have no children yet, and again, there is nothing set for the extents yet. And then we say for 1 to 8, so we have 8 children, and we say box.children is equal to children. Then we say the index is going to be equal to k, and then it says, so this is the index, which child are we talking about? This goes from 1 to 8. Right, so we'll probably be changing to Hsv as well, but right now we're using RGB. And then we say children of index.extents, and basically what we're doing is we're just making it so all of the children have, are going to be at some location within the other box. So for example, this big box is going from 0 to 1. But this little box is going from 0 to 0.5, and then 0.5 to 1. So we just split it up, and we give, 0 to 0.5 its own location, 0.5 to 1 its own box. So this is the idea. The extents of the box change depending on which, where you are, or which little mini box, internal box you're looking at. And then we do this function called naive bin of image and then children of index. Okay. So what this should do, naive bin in here, is it says initially we have nothing. We have no colors in the box. And then what we do is we go through every single pixel in the image. This is incredibly inefficient, but again, we're just trying to get something working for now. We go through every single pixel in the image. And then we say, if that pixel is in the box, if it's in the box here, then we say, If the box color is equal to nothing, then the box color is going to be equal to RGB is 0, 0. Otherwise, we're going to add 1 to the count, and we're going to say the box.color is going to be plus equal to the pixel value. So the pixel value is going to be RGB something, right? And so we add this all together. And then after naive bin, we should have some color associated with that pixel. So what I'm going to do is at the end of this, I'm actually going to print line. I know this is kind of dumb, but I'm just going to print line the children of index .clr. Okay, we're going to write that, and then we're going to go over here. Do I have an iPhone? No, I don't even have a phone. Like, I don't have an iPhone. I don't have, like, I use a Skype number. I just don't understand phones as a concept, so I don't have it. So let's go here. Again, it goes back to the whole minimizing dependencies. Like, phones are something that I was before easily able to remove phones from my life, so I removed phones from my life. Nowadays, I need phones for two-factor authentication, and I just use my tablet for that. So nowadays, I have a tablet, and then I have another tablet that I use that has a data plan. I know what iOS is, yeah, definitely. So let's go to, let's see, so we have octree. We have octree, divide octree takes in the image. So maybe I should do make octree of image. Make octree, quiltify, dot make octree of image. All right. I misspelled index. Write that, go over here, quiltify, make octree image. Okay, good. Don't worry, he's a doctor. What happens if you have to call 911? Yeah, so that's actually a big problem of mine. Yeah, so having to call 911 is actually a big problem of mine because I can't do that. I just have to ask someone else for their phone. So that is actually, so that's why I'm considering buying a phone recently. And what if you want to call your parents? Why don't you just text them? My parents prefer text anyway. Yeah, I don't have a phone at all right now. I haven't had a phone for 6 years, essentially. I mean, okay, so technically I did have a phone, but I didn't know I had a phone in Japan. So I was paying like $20 a month or something for a phone that I didn't know I had. I'm sure you could politely email the emergency service, buy a small, minimal, ancient keypad phone. Yeah, so my favorite phone, like actually in high school, I did have a phone. So let me just go to Shift O and let me do LG Lotus. This phone was a genuinely good, I loved this phone so much. The LG Lotus, I mean, I had the black version, but it was a really good phone. It had a full QWERTY keyboard. You could flip it up. That was the best phone. And now, like, you have all these phones that don't even have keyboards on them. Like, come on, what is a phone without a keyboard? I don't know. It's weird. Fire! Exclamation mark. Fire! Exclamation mark. Looking forward to hearing from you! Exclamation mark. He didn't even get to Blackberries. No, I didn't. But no, this was my favorite phone, and honestly, I really want this phone again. Like, I would love this phone. If I could get this phone again, I would get in a heartbeat. The only problem is nowadays I tend to do a lot of texting in Japanese. Not a lot, but enough. So this phone might not be perfect for me. For emergency services, you don't need any ISP services. They're callable from any phone, no matter what. Yeah, exactly. So I have like a stupid phone that I can call from. So the other thing I want to say is that there was a phone I was considering getting recently, the Microsoft Duo. What is it called? Surface Duo. Images. I was considering getting this one. And the reason I was considering getting this one is because I don't really have a need for a phone, but I do strongly have a need for a tablet. Because my entire, how do I put it? My entire research archive, like all of the papers I've ever read, are basically available in some form on my tablet right now. And I read a lot of papers, like just a lot of papers. And I find that reading papers on a tablet is basically the same as reading papers on paper for me. I was also thinking about getting an iPad Pro. That's another one. The iPad Pro is nice because you can get it with a phone number, so you can actually call people. And so then that would be like, I was thinking about taking the number that I have associated with my my, oh, what is it called? I have one particular tablet that I use that all it does is provide internet. So it's like a hotspot. So I could take the phone number associated with the hotspot, put it into my iPad so I could then call people. So I was thinking about doing that as well. The problem is I really don't like the Apple Pencil. Like, it just doesn't have any tactile feel to it. It feels like you're writing on glass. It's not nice, you know? So I was hoping for a better pencil. And I guess now it doesn't. I used to really strongly need palm recognition, palm rejection, but now it doesn't matter that much. Apple Pencil sucks and is over expensive. Yeah. So right now I have a Galaxy Tab Tab A, I think is what I have, which images basically just has an S Pen associated with it here. So I just pull out the S Pen and I type on it. So yeah, it's nice to read papers on. I quite like it. You can get tablets with SIM cards, but you look like an idiot holding it next to your ear. Meh. Maybe. That was the other reason why I was thinking about the Duo. I mean, the Duo is kind of a nice. It looks nice. Like, genuinely speaking, it's one of the nicest phones I've seen. And because of that, I have been thinking about getting it. Like, it looks good. Like, you cannot deny it looks good. The only thing that looks bad about it is the fact that it has this stupid Microsoft logo on it. I really hate Microsoft, but this is a genuinely good looking phone. Like, and it has a really cool, like, I don't know. Like, the reason I don't want the Galaxy Fold Z or the Galaxy Fold is because I mean, maybe the newer Galaxy Fold is fine. Galaxy Fold Z could be better because it's the second generation Fold. But also it's I don't know. Okay. Let's try this one. No. I was getting back to that. Sorry, I missed it. This one's not bad, but again, I want something that works as a tablet. Oh, this is the most annoying website I've ever seen in my life. Holy cow. Wow. That is annoying. Oh no. It gets more and more annoying the more I scroll. This is the worst. Oh no. I'm not buying this just based on the website. That was the worst website I've ever seen. Oh, geez. It's like an Apple website. Man, that's awful. Anyway, let's go back to quilting things. Actually, wait. I went over here for a reason. What was the reason I went over there? I don't remember at all, actually. Yeah, I don't remember at all. Okay, so this is interesting. When we went through and we outputted the color for each of the children here, we're outputting, first of all, 2 different colors and then a bunch of nothings, which isn't great. Don't look at the Microsoft website. So let me change our image. So our image is now going to be equal to actually just rand of 100, 100. Okay, and now let's try. Let's do 1 second. I think quiltify.make octree of image. Okay, so here, fine, fair enough. We have a bunch of values. This is about what you'd expect. This is fine. What is 1 plus nothing in Julia? I don't know. An error. If that helps. Okay, so this is actually kind of what I expected for the octree to return. So now my question is, if I say tree is equal to that, and then I say tree dot children of 1 dot color, we get that, and of 2 dot color we get that, and of 3 dot color we get that. Okay, fine. So does this work? It just didn't work in that case because I'm bad at coding. Let's see. So now we're going to try img2 is going to be equal to quiltify.quantize8. And what happens if we look at these guys in here? So here we have 0.506, 0.506, 0.506. Okay. So the color set here, so the octree, all the children in the octree have a different value. Okay, that's good. However, the color set, for some reason, is not pulling the appropriate colors. The color set is all returning the same values, and I don't exactly understand why. So I guess I'm just going to go here, and we're just going to say print line box.color Go over here, and now we're going to do image 2 is equal to Quiltify again. Oh, well that's interesting, isn't it? Maybe because we should have done the following. We weren't recursing. Let's see what that does. Oh, already it's looking better. Okay, well that's fair. Let's go ahead and remove those unnecessary print line statements. So we're just gonna dd there and look for next print line. Print line. All right, perfect. dd there, write that, go over here. Image 2 is equal to Quiltify. So now we're gonna do ImShow of img, and we get a bunch of random noise. Perfect. And now if we do img2, we should see again a bunch of random noise. So let's plot img1 minus img2. img1 minus img2, and this gives us all the changes, and it is saying basically every pixel has been changed. That's kind of what you would expect. Okay. So blue finally exists. Can you do 1 plus true? I don't know. Yes, you can. It's equal to 2. So if anyone's wondering, 1 plus true is 2. One interesting thing is that false is a hard 0, I think. So if I do a nan, I think that exists. So nan times 0 is going to give you nan, but nan times false is going to give you 0. So that's an interesting bit. So just in case anybody wants a hard 0 that also works on nans, false is that 0. Let me get some water. Okay, so now we do officially have a working color quantization method. Nothing times false. It's still an error. You can't. Why is it a float? Because false is a float. I mean, I don't know. Julia naturally does everything in floating point if it can. So that's why it's a float. That's my best answer for why it's a float. Okay, good news. It does seem to be kind of working. So let's go ahead and DD here. Now let's just take a random image. Let's take a rainbow. Okay, so rainbow. Let's take a pride flag. The reason I want to do something colorful is because I want something that, let's do images. There has to be like a good image of a pride. Yeah, look at this one. That's a nice one. Let's go ahead and do save image, and we're gonna say pride dot. What format? Do it there. And it's download.jpg. Okay, great. So let's go ahead and remove that. And then let's move it over here. So now we're going to, I actually think nan is a float. Oh, it could be actually, you might be right. Let's quit here. Right and quit here. And now I'm going to move downloads and then QWE download here, and we're going to say pride.jpg, I believe. Yep. Okay. So now over here we're going to say img is equal to load pride.jpg. Okay. So now we're just going to try to quantize pride and see what happens. Okay. So now we're going to do imshow pride img. And we should just see the pride flag. Perfect. And again, I'm choosing a colorful image because the way that we're currently doing the box choice is we're just saying we split the boxes up into like red, green, blue, all this kind of stuff. So we just want something, so we just want to make sure we don't get any nothings. So now we're going to do img2 is going to be equal to quiltify.quantize8. It is doing something. It is taking a bit longer, but it worked. So now if we do imshow of img2, what do we get? Actually, not a bad effect. This is kind of what I was expecting. That's pretty good. I mean, it is weird that the sun is gray, but that is actually a really cool effect. Come on. That is so cool. Like, you see the outlines here. You know, you see the darkness there. That's pretty cool. I like that a lot. Okay. And this is compared to, so now I think if we just do, let's imshow img minus img2. Ooh, look at that. That is interesting. Okay, this is actually pretty good. Chat pause due to scroll. Oh, I'm sorry, I'm not seeing chat. Let's go here. It ripped a hole in the flag. Looks like a beautiful piece of art. I thought it looked pretty good, didn't it? It ripped a hole. Dude, upload this to DeviantArt or something. Wait, just tuned in. This is sick, isn't it? It's super cool. I was not expecting it to be that cool. Let's look at the quilt, actually. So I'm going to do, img is going to be equal to load of quilt.jpg. And now let's do img2 is quiltify quantize, and let's see what it looks like. That was surprisingly cool. This one's not going to be as cool, I'm pretty sure. No, it looks dumb. This one looks dumb. It just looks like a worse quilt. I mean, it's not bad, but the other one looked really cool. Okay, so let's do, let's keep the pride one as the, well, no, it doesn't look cool if it's up there in the corner. So we should do something that's maybe a bit, what if I actually do a rainbow? Let's do an actual rainbow. Rainbow. Aha, okay. Rain. All right. Rainbow image. Let's see what we got here. Images. That's a pretty cool image. Oh no, that's a cool image. Oh, see, now I'm just looking at cool images. Welcome to Simuleos, the stream where we just Google rainbows. I'm actually, that's a bit big, but let's see what happens if we do this one. So we're going to, I think we can view file. I think. Oh, it's over here. And let's see what happens if we download, save the image. Yep. So it's rainbow sky fb.jpg. And so now we're going to move downloads, rainbow sky here, over here. Now we're going to say img is equal to load rainbow sky here. And now we're just going to do, what are we going to do? Give me just a second. I have to think about that. img2 is going to be equal to quiltify quantize and see what happens. It's not actually visible through the flag in the original, so I take back my criticism. Yeah. This is taking a while because the image is quite big, but also remember the image is quite big. So it's relatively quick considering that. And now we're going to do imshow image2. That doesn't look as cool. It looks worse. The flag was the best one. All right, I'm going to try one more time, and then we're going to get back to doing some programming. But I'm happy enough with this. I want to try this one. So let's do this one. View file. And let's do save image. Sure. It is rainbow wallpaper. So now we're going to move downloads. Yeah, we can do more levels, but I'm not. Yeah, we can do more levels. Rainbow here. Let's go over here, and img is going to be equal to load of rainbow wallpaper there. Image 2 is going to be quiltify that. Okay. One of Simuleos gets distracted by passing butterflies. I don't get distracted that much. I'm testing it out. This is me making sure it works. Can we see the flag before and after again? Yeah. Oh, sorry about that. I was embarrassing. Image 2. That one looks cool. Okay, that one looks really cool. Okay, doesn't it? I'm show image. So here's the original image versus the quantized image. Let's see if we can put them both on screen. Maybe up here, and then, I don't know, over here or something. This isn't the best way to show them, but come on. Isn't that cool? I think that's super cool. Please upload high quality image. I can put this, yeah, I can put this on the Discord if you guys want to use it. I think that's really cool. I'll put it on the Discord. I'm saving both of them. That's cool. I'm a fan. Every time I do color quantization, I'm impressed by it. So let's do save, I believe, and then we're gonna say img2, and we're gonna save it as rainbow wall 2.png, sure. Join path jpg. Oh, probably because I did it backwards. img2. Does that work? All right, give it a second. Right. So please upload high quality images. Yeah, so I should have a new wallpaper too. So let me do Mirage, rainbow, wall 2.png. Okay, so that's that image. And I'm just gonna go ahead and put that on Discord right now. Oh, I don't have Discord up because my computer turned off. So let me do that. So code, I'll go to off topic, and then I'll just paste it in here. So let's do Rainbow Wall 2, open, upload. There you go. That's it. It's on Discord. If you're not on Discord, here's a link to Discord. I'll talk about how it works in just a second. Let me also do the pride flag, because I quite liked the pride flag. I thought that was really cool, except for the fact that the yellow wasn't very yellow. So let me try that again. So let's do img is going to be equal to load. What do I have here? What ls? So it's going to be called pride.jpg. Okay. And now we're to say img2 is going to be equal to quiltify.quantize. And let me take a look at that one again. I feel like we should load pride.jpg. No, I want to do imshow image. So that was the original image. And now if I do image 2, we get the new image. Okay. So the reason I like this is because it does highlight like it looks cool. It's just that this needs to be not gray. The question is, why is it gray? Because to me, I would think that needs to be more white, right? So here's the original flag. And here's the quantized flag. I still think that's a cool effect. Like, you just don't... It's just that gray is a bit too gray, you know? So I feel like I want to change that gray to be white. So what I'm going to do is I'm actually going to modify that one. I need 9 colors for the sun. Maybe you're right, actually. Let's do that again. So we're going to do image 2 with quantize, and let's do 9. And see what happens. And so now we're going to do imshow image. Oh, that already looks better. You're right. So now we're going to do image here. I'm going to make that big. So here's the original image, and here's the quantized one. This is so cool. Every time I look at it, I'm just amazed by it. I love this so much. Okay, yeah, okay, I'm happy with that. I mean, we can increase the colors as well. Let's do 16. Actually, 17. We'll do 17. And I'm going to call this image 3. I'm doing 17 because I want to do 2 layers deep, and then I also want to do 2 layers deep into the tree, and then I also want to do the big box that covers them all. So if we do imshow image 2, there's that one. Image 3, there's that. Image 3 looks the same as image 2, doesn't it? So I could have something wrong. Image. Okay. So I still probably have something wrong here. So this is that one. That's that one. And that's that one. Okay. Yeah, image 2 and image 3 look the same. So oh, no, they don't. There's small speckles here. There's like little specks here and there that are slightly different, but it's really hard to tell. But overall they look similar. And then here's the original image. Okay, is this color quantization? Yeah, it's color quantization. A while ago I posted a video on YouTube. I think if I just go here, and then I go to videos, and then I go to sort by most popular. How do I grab this? I just wish I could grab that, but I can't. So we're gonna go here, there, and allow the website to show notifications. Yes, I don't know. Share that, and we will grab this guy, and then we'll paste it there. There you go. That's what I need to do. So that's my video on color quantization I did a while ago. Here's me color quantized, by the way, just in case you wanted to see me color quantized. So yeah, that's where we're at now. I'm happy enough with what we have, but obviously there's a lot of work to be done. So let me delete all these guys, and let me scroll up here and see what we have. So, oh, well, isn't that interesting? I said I wanted 17, but 1, 2, 3, 4, 5, 6, 7, 8. There's still only 8 colors. Why are there only 8 colors? So maybe that's one thing we have to fix. So let's first fix it so that we can Nota MN thing. Thank you so much for following. Really appreciate it. So let's go into Quantize.jl, and then we're gonna do, let's see. So the color number is gonna be the total number of elements in the color set. So then we find the color set, find color set of 17. So we should have 17 elements in our, oh no, we're not outputting the color set here. We're outputting something else entirely. So this is the, what are we outputting there, actually? Where's our print out statements? We are printing out, oh, the child colors for, oh, I see. My max level must be set to like 1 or something like that. Where's our make awk tree here? Make awk tree of image. So let's set this so we have a maximum number of levels. So here, levels. And then down here, we're going to do levels. And then down here, we're going to say make awk tree with a particular number of levels associated with it. And the levels are going to be equal to, let's just do like the next power of 2. So we're going to do color num -1. Okay. And then I think we want the log base 2 of that. So let me do log 2 of 16. And that'll give us 4, and that's what we want. Log 2 of that. We might need to cast that onto an integer, but I think that'll work okay. So now let's try quantize as 17. No method matching divide awk tree. Divide awk tree. Where are you? Divide. Make tree, divide awk tree. Levels. I see. Divide awk tree. And then there must be another one here. Divide awk tree there. Divide awk tree there. Max level is an integer. Yeah, I need to cast it onto an integer. That's what I thought. Okay, so let's cast that onto an integer. So we'll say, I think I can just do int in here. I think that'll do. No method matching log2 type int64. What? Okay, that's fine. We'll cast it onto an int out here. Okay, try that again. Okay, this seems to work. Now in principle, we should have 17. That didn't look like 17 to me. That looked like it still was 8. All right, we'll keep working on this. Oh, is it an awk tree? Never mind. So what is the data structure? What is, it is an awk tree. It is an awk tree. So what is the data structure like with that? It is an awk tree. I have a basic understanding of an awk tree as a node with 8 children, but I have a hard time associating with color quantization. Right, so what we're doing here is we are essentially, in 3 dimensions, we're taking our color space, which is R, B, and there's another dimension for G. And what we're saying is that every single point here has every single pixel has some color associated with it, right? So we distribute that on RGB space. And then what we do is we have some giant box, right? And that's the big root node. And it has 4 sub-boxes. And those sub-boxes have sub-boxes associated with that. And they have sub-boxes and sub-boxes until eventually every single pixel has its own box. And so the idea is, this right now is a quad tree. In 3D, it's an awk tree. There's just another dimension. So instead of seeing 4 kids, there's 8 kids. So it extends out another dimension that way. Sorry, I drew this for simplicity, where we only have R and B, and then there's something in the other direction. So again, you've got a big box that has little boxes and little boxes inside of it until every pixel has its own box. And the idea is we just pick the n most populated boxes. That's the idea. And those n most populated boxes will have some color associated with them, which is the average of all the colors inside of that box. So that's kind of how it's done. Right now it's super inefficient. We're kind of just working things out, but you know, step by step. So, yeah. I hope that made sense. Do you still use an octree for color quantization, or is it a quad tree? It is an octree for color quantization, but for simplicity, showing it was a I showed it as a quad tree because that was easier. Okay, so let's see. We have number of children greater than max level. So reading in max level. Let me print out the max level here and see if I'm doing something wrong here. So let's say max level is going to be equal to this guy. And then down here, we're just going to print out max level. Okay. And let me change all the levels here to be just max level. Okay. There should be another one up here. Max level. I did it again. Okay, so levels shouldn't exist anymore. It does not. Okay, so now I'm going to print out the max level and just see what we have. It should be... let's just do it. Missing comma or okay. What's the issue here? The error is in... It is in parsing.jl line 45. That doesn't help me. That doesn't help me at all. Okay, that error message was not very good. Probably if I did using quantize again. So what if we do revise.errors? What do we have here? Missing comma, it is in 109. Print line. That. Okay, so it's 4 maximum levels, which says to me if 4 is a maximum level, it should have 1 as a maximum level, then 2 has 4 elements, and then 3, bad terminology aside, it sounds like your entire set of space area is the bounds of your color values, assuming X, Y, Z to RGB, so you're looking for clustered nodes, essentially. No, yeah, you're right. Also, my terminology is bad. Don't think that my terminology is better than your terminology. It's also bad. But yeah, that's exactly what we're doing. We're kind of looking for clusters in color space. And color space is, in this case, a Cartesian grid where R, G, and B, or X, Y, and Z correspond to R, G, and B. That's what it is. So if you're used to like galaxy simulations or something like that with the Barnes-Hut method, I really want to try, I just thought of this. What happens if we do a galaxy simulation in RGB space? Hear me out. Hear me out. Okay, just let me just hear me out. Journal, new page before. Okay. So here's how galaxy simulations work. I'm going to do it in 2D, but in principle, this could be in ND or 3D, right? Okay, so we have a bunch of particles. Let's just go here. Okay, just hear me out. Hear me out. This is really dumb, but just hear me out. We got a bunch of particles, right? A whole bunch of particles all over the place, right? And in principle, each of these particles interacts with all the other particles in the simulation, right? You have F is going to be equal to the sum of all the forces, mass times acceleration. So this particle here is going to feel forces from every single other particle in this simulation. So if you have a lot of particles, then all of a sudden the simulation is incredibly slow. But what you can do is you can do something called an aux tree here, where basically you split it up, and you split it up again, and again, and again, and again, and again, and again, just like we're doing with color quantization here, until every single particle has its own box, essentially. And then what we say is, well, if this particle here is really, really far away from this entire group of particles over here, we then assume this entire group of particles is just one big blob, right? And that way we don't have to deal with the computational complexity of every single individual bit. Instead, we have to deal with it as a giant blob. So if instead all of these particles are moving around in RGB space, so this is R and this is G, and then we have a third dimension for B, then all the pixels in the image would be changing colors based on a galaxy simulation. That would make a really weird plot. I don't think that'd be weird. At what point is it Unix born worthy? I don't know. I mean, we'll see. Okay. Paste. Enter. That looks really cool, man. That looks really cool. And also, your computer name is by the way, because you use Arch by the way, and your username is God? This is cool. Wow. But also, like, that looks really cool, man. Like, genuinely impressed with that. Okay, let's just keep going over here. Oh, it's nice. I'm a big fan. Just randomly installed once on a VM. I guess I'm not because of VM. Well, it's probably fine, right? I mean, have you seen my desktop? Am I Unix? Like, look, here's my normal. Sorry about this. This is my normal desktop. This is what it looks like. It's just black, like literally just black. Is what I do. This is my normal. I like it. I like it. It's nice and clean. You know. So. A bit of transparency, Kava Music Visualizer and Matrix Terminal. Okay, so what we're trying to do right now is figure out why our divide awk tree is not dividing as far as we want it to divide. So let's go. So we have divide awk tree here, and we say if the level is greater than the maximum level, then we return. All right, but we're not greater than or equal to the maximum level because let's output level. Okay, so now we're just gonna make the awk tree now. So we're gonna say make awk tree quiltify.make awk tree, and we're gonna do image should work. Oh, and then level is gonna be 3. So we have 1, and then why did we only go 1 level deep? It's because our children.extents creating new extents. Oh, I only allowed it to go 1 child deep. That would explain it. Right, so we do the naive bin down here. So the naive bin is there. And then we print line children index.color. So that's fine. And then after this, what we do is for each child, we do the naive bin. And then we need to call divide awk tree on each child. On children of index. Children of index. Give me a second. I need to think here. We need image. Children of index. The level +1, and then the max level. And that should be right. So if we go over here and we do make awk tree image. With the max level equal to 3. 1, 2, 3, 3, 3, 3, 3, 3, 3, 3, 3. Good, 2, perfect. Great, that's what I want to see. Wonderful, beautiful. All right, so now we should be able to quantize a bit more. So let's go back to that flag thing that we did just a second ago. And now let's... 2, 8... okay, so I had 64 colors in that one. That makes sense. Because it goes from 8 to 64. Right. Okay, well anyway, let's do img3 is going to be equal to quiltify 17. And so, okay, that's, what is 8 to the 4th? Why did I say 17 again? G down here. So I wanted the max level. So the color set. Why am I making so many boxes? I'm just trying to think here. So if we go 4 levels deep, then that means we have 1 big box at the start, and then we have 8 smaller boxes, and then we have 64 even smaller boxes, and then we have a lot of even smaller boxes, right? Like, what's 8 to the 4th? I think this is going to take too long. Yeah, I think that's going to take way too long. If I want 16 colors, A to the 5 minus 1, right? Yeah. Well, wait. Oh, that's because we're not log 2. We're log 8. Is there a log 8? No, there's no way. How to do logs? Yeah, okay, I remember now. I was doing log 2, but in fact, we actually want log 8. I understand. So how would I do a log 8? So we want the cube root of divide the log 2 of 8. Yeah, I guess. Wait, so 16, so log 2 of 16, right? This is going to give us 4.0. Does that only work for natural logs? Is not log 2 divided by 3. So it's going to give us 4.0. What am I trying to do here? I need to think. Is it log 2 divided... How do exponentials work? Oh, man. So log... So the log base 2 of 16 is equal to 4. Because 4 squared is going to give you 16. All right, we're getting there. So what we're looking for, if we want 16 colors, we want to quantize to 16 colors total, right? So what we're looking to do then is we need to make it so we have enough boxes so we can find at least 16 colors. So that means we have 1, 8, 64, what is 256, and so on. So we need to get to this level. So we need to get to the third level. So if I say we need 16 colors, and in fact, I say we want 17 colors because I also want the overall average. So we'll say 17 colors, but whatever, 16 colors. Then we need to make sure we're greater than 8. So the log 8 is equal to log 2 divided by log 2 of 8. Okay, that's probably right. That sounds right, right? So we do log 2 divided by log 2 of 8. And then we seal that. Int. That's, I think, what I want. Perfect. Okay. So we are going to seal of int, and then we divide that by log 2 of 8. That looks right, right? Okay, perfect. All right, so let's try this again. So we're going to try image 3, 2, 1. Okay, so this should be 64 colors. Was it 64 colors? That looks like it was not 64 colors. That looks like it was... Oh, I probably want to do a +1. Just making stuff up as we go along. Okay. Thanks, Alexor, by the way. Really appreciate that. So, yep. Sorry, I'm dumb, guys. Like, I'm trying to not be, but like also it's really hard not to be dumb. This is gonna take a second. Oh, never mind, it's done. So let's do I'm show of image, just image. This is gonna be the pride flag. Image 2, which is gonna be the pride flag. Image 3, which is gonna be okay. Well, doesn't look as cool. It just does not look as cool. Okay, so here was the original image. Here is the first color quantized image, and here is the second color quantized image. Let me do 65. I've got a feeling the reason it did that was because the way in which we're choosing colors right now is that we are going through and we're just like, we're doing a depth first search to select all the colors, and we're just naively picking whichever color we want. So we're not even trying, we're not counting which boxes are the most populated. We're just picking 8 boxes or 16 boxes. So let's try image 3 now. That one looks so much better. Oh, that looks so cool. Okay, so now we're gonna do image 2, and we're gonna do image 1. Oh, that looks so much better. Oh, that's way better. Okay, so here's that image. Here's that image. And here is that image. All right, I'll buy that. That's not bad. I mean, I'm not gonna like buy it. I'm not gonna pay money for that. But like, you know, that and versus that. I still think this one's cooler. But like, you can see it transition right? So there's the original image. There's 64 colors, and there's 8 colors. I think this is cool. I mean, look, I realize that probably it is weird that I chose a pride flag, right? Maybe, but I wanted something that had like a lot of colors, so I was like, let's just do a rainbow or something. Let me try that rainbow image as well, because I think that rainbow image is quite cool. So let's give it a go. So we're gonna do img is gonna be equal to rainbow wallpaper HD, and we're gonna say image 3. This is gonna take some time, guys. I am sorry about that. Oh, this is going to take a long time. And the reason is because of how we're naively binning the pixels. Start animating stuff using color quantization. Oh, that my original video had color quantized. You're right. So I guess ideally, I would love to be able to do this fast enough that we could... I would love to be able to do this fast enough. Oh, some of these are nothings. That's not good. That's not good at all. But I guess nothing is black. So I'm hearing correctly, it sounds like you're using an octree like a quad tree, where instead of splitting your 2D XY into 4 boxes, you're actually splitting it into 8. Yeah, octrees are... No. Thank you for asking the question. An octree is an extension of a quad tree into 3D. So it's literally the same thing as a quad tree. It's just with a third dimension, so it's split into 8. Because a quad tree is a quad tree because you take X and Y, and you split X in half and Y in half, so you get 4 boxes. So an octree is an octree because you split X in half, Y in half, and then Z in half, right? And that means that you get 8 boxes after splitting them all up. But thank you so much for the questions. Like, if I did a bad job of explaining that, I did a bad job of explaining that. So I need to go back and fix that. So, okay. Hex tree for RGBA would be interesting. Hex tree. I don't even know what that means. So let's do image show 3. I don't know if that's cool or not. Let's do image... Oh no! I meant to save the... It's okay. This is fine. So let's do save rainbow wall 3. That PNG. Okay, so let's just take a look at all 3 of them back to back. So we're gonna do quit here, mirage, rainbow wall. Well, actually, let's move rainbow wallpaper to rainbow wall dot p. Oh, it's JPG. It's fine. Okay, so let's do mirage rainbow wall dot JPG. Okay, so here's the original image. Okay, let's make that bigger. Right. So then rainbow wall. Okay. Rainbow wall, rainbow wall, rainbow wall. Oh, I guess I want to do... Why is this one in the middle? I'm confused. Rainbow wall 3, 2. Rainbow wall, rainbow... Oh, wait, why is that... Wait a minute, what just happened? Where's... This is the original wallpaper. Rainbow wall 3. Oh, I must have outputted the wrong one. So this should do image 3. There we go, perfect. So now we have... Go that. Over here, open that. There we go, that's what I want to see. Perfect. Let's move this over here. Move that over there. Okay, so here is the original image. Here's slightly quantized, and here's like more quantized. I feel like... I think that one's actually the coolest. I'm not gonna lie, that one's actually the coolest. So what I was hoping to do then would be to... Okay, so we've got a lot of things we still have to update with the color quantization, but I'm happy to say that we're getting there. Hey, how are you, Nixitive? I hope you're having a great day. I might just have to play with it to figure it out myself. Yeah, it takes some time. Sorry about that. Hex tree for RGBA. I might just have to play with it. There's a lot of things in math where a lot of math fails when you do stuff 5 times or more. A lot of times it's nice to fit, but you overfit when you have more variables and you have to keep majority of the error. Okay, I think that's cool. Like I'm a fan of this. Yeah, man, it looks so cool, doesn't it? I mean, look at that. I mean, this one also looks cool, but that one looks really cool. Okay, anyway, so let's go ahead and move on, and let's do... I'm actually going to turn this into a video to have playing in the upper left-hand corner, and then we'll go from there. So let's do... let's go ahead and move rainbow wall.jpg into, let's convert rainbow wall.jpg into rainbow wall 0.png. Okay, so now let's do ffmpeg dash I rainbow wall. I think this .png out rainbow wall.mp4 d 1d. Oh, I misspelled rainbow. All right, let's try that one again. Oh, and I think it's just that. Okay, so now what we want to do is make it so the rate, I think it's -R60. Yes. And so let's just do mpv rainbow wall.mp4. Okay, that was not what I want. Probably 1. Huh? Why was it only 1 image? Doing great, got compression working from my file sharing site, and started streaming. Interesting thought, if you could use HSL instead of RGB, would you get the exact same result? I don't know, that was something that we wanted to try. Okay. Wait, what? For my file sharing site. Okay, so that didn't seem to... Okay, that's still just 1 image. So what if we do this? ffmpeg. I have to Google this again. I always have to Google this. So let's do ffmpeg images to video. Are the other files .png? Yeah, they should be. Yeah, rainbow wall 0, 1, and 2. Are they spelled differently? No, they all seem to be spelled the same. So ffmpeg r image to picture 04d 04 01d. I'm missing a wall 1. Oh, you are correct. Oh, you are definitely correct. Move rainbow wall 0 to rainbow wall 1.png. Try it again. 1D. Yep. Now let's do MPV. Okay, that was only 2 images, I thought. Or am I being dumb? I don't think I'm being dumb here. I think that's just 2 images. Let's do Mirage, rainbow wall 1.png, 2, 3. Oh wait, probably should do this. Yeah, okay. Let's do some more. I wanted to create a very simple video, you know, like that's all I wanted to do. So let's go ahead and move move rainbow wall 2 into rainbow wall 4.png, and then move rainbow wall 3 into rainbow wall 2.png, and then move rainbow wall. Oh my gosh, sorry about this, guys. 4.png into rainbow wall 3.png. Okay, so now I'm going to try it one more time, see what happens. ffmpeg. Can I just do this? Wait, where's the last image? Is it just skipping the last image? Oh crap, I just deleted the terminal. Okay, so let's do this. Make this huge. Move that over there. Move this up just a hair. There we go. CD projects, Quiltify, Alice here. Okay, so let's just CP rainbow wall. This is a dumb solution, but it'll work. Rainbow wall 4.png. Let's run the last ffmpeg command. Yep. And now if we do MPV, it should play it. No, wait, what? Where'd it go? I don't understand. Okay. Okay, there it is. Perfect. Okay. I don't understand why that did anything, but whatever. There we go. Perfect. Now we do it one more time. Okay. Now this should be fine. There we go. So there's that. There's that. There's that. Great. I just wanted to have that looping in the upper corner. So we're just going to Control C here. MPV rainbow wallpaper .mp4 loop 0. Okay, we're just gonna have this playing up here, just so we have something playing. There you go, perfect, wonderful. Maybe something like that. There we go. Move this down. Okay, that was way more effort than it was worth. Okay, let's see, Jessica Mack, how are you? I hope you're having a great day. If you guys don't know Jessica, she is a wonderful streamer. Makes a lot of really cool video games. Check her out. She is a really, really cool person. And if we have not already, if we haven't rated her recently, maybe we haven't. But also, she's cool. Check her out. She's really cool. What are you guys working on today? Let's see. Also, Greedy Row, thank you so much for following. Okay, so as a brief introduction, hello, my name is Dr. James Schloss. I realized I got to the raid just maybe a minute late. Sorry about that. I am currently working on a new method for the algorithm archive. Let me go there, the arcanealgorithmarchive.org. So algorithmarchive.org. So basically, I'm working on a new method for this, for color quantization. The algorithm archive is basically a place for you to learn about algorithms. So here is a chapter on Gaussian elimination. The idea is you can switch between whatever language you feel suits you best. So if you learn best in C++ or Haskell or JavaScript or Julia, you can pick whatever language you want. And the idea is that we hopefully teach the algorithms in an intuitive fashion. So like here's an animation that we use to teach Gaussian elimination and stuff. So we're getting started on this. We're nowhere near where we need to be. In addition, I also have a YouTube channel. In fact, I think that's the video you guys want to look at for color quantization, which is what we're working on today. So what you're seeing up there in the upper corner is actually is a color quantized version of the original image. So the idea with color quantization is that you take the image and you basically put all the colors into some sort of three-dimensional RGB space where instead of X, Y, and Z, you have R, G, and B, and then you figure out which colors are essentially the best colors to represent the image by. Like which colors do you need to keep, and which colors can you get rid of without really people noticing. And the idea is that you just pick those colors and you replace all the colors in the image with their closest approximation of the colors that you've chosen. So you find a set of colors, like maybe 8 colors, maybe 16 colors, maybe 64 colors, doesn't matter. And then you basically take the image and you cast all of the pixels into those 8 colors. So that's color quantization. What we'll do after that is we will basically make a quilt pattern for that. Are you writing shaders? No. I think this would actually be too complicated to do via a shader because you have to do a lot of tree traversal and such. So I don't know if you can actually use shaders for that. Did you code that graphic in the top left? Yes, I did. That's what we just finished doing. I could use this so much in college. We're hoping that it becomes a really useful resource. So I'm also teaching a course at MIT this term for Julia and computational thinking. So a lot of that will kind of bleed into the streams that I do. Like, for example, we just finished a stream on epidemic models, which will be going into that class. Trying to get the first part of the game flowing better and bug-free. Oh, cool. Yeah, I'm really happy that you're here. And again, if you guys have any questions, comments, concerns, anything like that, feel free to let me know. Outfrost, thank you so much for following. Also, Luch Labs, thanks for following. I don't know if I said thanks for that. Quilt time. So we're actually a bit further away from quilt time than you might think. So what are we doing here? That's also another question. I'm creating an application to create a quilt. I know that sounds really lame, but hear me out. So let's say we have an image. It doesn't matter what the image is. So I'm just going to draw a tree with my wonderful artistic skills. Okay, I did this earlier today and I failed miserably. This is actually broccoli. I actually just drew broccoli. So I'm just gonna draw a fork again, and we're just gonna say the image is some guy eating broccoli. All right, that's our image. So the idea here is that I want to basically find a way to represent this image in such a way that you could turn it into a quilt. So what we need to do is two things, or three things actually. One, we need to quantize the colors, right? Which is to say, we want to find a minimum set of fabrics, or not minimum, but we want to find a set of fabrics that allow for us to represent this image and have people still recognize it in a cartoony fashion, right? Two, what we need to do is we need to then quiltify it, which I'm going to call quixelate. Essentially what we need to do is we need to transform our image into a set of quarter squares, which are going to be useful for, turning it into a quilt, right? Because quilts, you have like squares, and then these squares can be split up into additional triangles. And so the idea is, if you want to make an image, you could probably use squares for the most part, but you might need to split it up into quarter squares or half squares or something like that. And then the third thing we need to do is add texture, or basically apply the fabric. Because, if you want it to look like an actual quilt image, rarely do you have just a blue fabric. Usually it's blue with some sort of pattern on top of it. So we want to make it so that you can just make it look like a quilt in the image itself. So there's a lot of stuff here that we have to do. Right now it's all running on the CPU. We're not doing any shader logic or anything like that. In principle, we could, but also we're interested in providing a kind of simple implementation of the algorithm, which requires octrees and tree traversal and all this kind of stuff, which is not naturally good or is not particularly well suited for GPU computing or shader logic or anything like that. So we might end up, I don't know how to put this, but we might just keep typical CPU programming and not focus much on the GPU side for now. So yeah, the other thing that we just made, I don't know if you guys saw this or not, but we also did the same with the pride flag, which I thought turned out really cool. So here, let me show you, I think I need to show you the original flag as well. So image is equal to load, pride.jpg, and then if I do image show of image, I thought this one turned out really cool. I mean, about as cool as the thing up there. So up here, we're going to do that. And then over here, we're going to do this. So basically, like, here's the original flag that we had, and here's the quantized flag. You can see that, like, we have like a bunch of, kind of an outline and stuff like that. So I thought it turned out really cool. Again, we're just at the first step of making that quilt, which is a quantization step. A quilt is a quilt. This thing. This is a quilt. That's what it is. It's literally a physical quilt that you could sew. Like this is what it is. I gotta watch the color quantization video. Yeah, feel free to do so. I'm hoping that it's useful. That was one of my first, it was a long time ago since I made that video, and it's still not available in the algorithm archive, so I kind of need to fix that. So this is an application that I'm doing that I think will be really cool. And I think I also think it's like one of those things that could get a lot of YouTube views as well. So I'm kind of thinking that I would like to, I want to turn it into a video, kind of, that kind of stuff. So that is a quilt. A quilt, a warm bed covering made of padding enclosed between layers of fabric and kept in place by lines of stitching typically applied in a decorative manner. Yep, that's what it is. Let me get some water. And then we're going to hop into it. So there's a bunch of other things that we need to do. Now that we have a basic, incredibly basic form of color quantization working, we're just going to work through the list of to-dos because we've got 8 to-dos to go through. And so we'll just knock out whichever ones we think are easiest, and then we'll attack the harder ones probably tomorrow. Okay. But yeah, there was the question earlier. Some people came in and asked what a quilt was because they thought it was like a computer science data structure, but no, it's very far from that. We're literally making something that we could sew. And again, I know that sounds really weird, and it's it's not clear why I would want to do that, but at the same time, I think it's cool. I just think it's really cool, and I just wanted to try it. So it's one of those just fun side projects that I decided to do. Okay, so let's go here and let's open up. Where were we? We're gonna open up a file, whatever the file is that I want to open up. I don't know what that is. Give me a second. I just need to think about things. All right. See, this is a situation where I should have just, there we go. Quantized.jl. Okay. So we have 5 to-dos up here, and then we have another to-do, 1, 2, 3, 4, 5 down here, where we want to use breadth first search instead of depth first search. And then we have another to-do down here. So there's 7 to-dos that we have to get done. The first thing I kind of want to do is see if using HSV color space is any different than using RGB color space, because HSV color space is, in principle, I think it's an additive color space, so it's a little bit, it's just nicer to use than RGB color space. It's literally what you thought. Yeah, so it is what you thought. Like, there's no, we're not pulling wool over anyone's eyes. We're doing exactly what we said we're doing. We are coding up a quilt. That's what we're doing. It would be a computing term. Is it a computing term? Am I dumb? Is quilt a computing term that I should know? Okay. So right now we have all these to-dos. Let's work through them, see which one we want to attack now and which ones we want to attack next time. So first to-do, the quantization may fail if there is no color associated with each sub-box. So for those of you guys who just jumped in, the way this octree, ooh, hello, I'm so sorry about that. The way this octree works is that we basically take a box, right? It's in principle in 3D, but here we're showing it in 2D. And the idea is that we have red on one axis, blue on another axis, and green in the axis out here. And each pixel is some dot on this axis. It's some color, right? And so the idea is, sorry about that. The idea is we basically split this big box up into 4 sub-boxes, and those 4 sub-boxes are split up into further sub-boxes, and those sub-boxes are split again and again, until essentially every single pixel has its own box with its own color associated with it. Each box has a global, or rather, has an average color associated with all of the other pixels in that box. So the idea here is that, like, this box, the color associated with this box is an average of these 2 colors put in here. So it's like somewhere in between these 2 colors. And so the way that we're currently doing this is we find a set of boxes. So here's like maybe this guy, and then 1, 2, 3, 4, and we say, okay, let's just use 5 colors to quantize, and we're literally just going to pick the top box and the 4 sub boxes. So the average of everything, and then also the 4 children of that guy, and that's all we're doing. So to create the flag that I just showed here, image 2, this is just 8 colors of our original quantized image, which is this one here. So this is the original image, and over here is the quantized image, right? So I think the quantized image is actually a really cool effect, but also, like, again, there's a lot of work that needs to be done. It is, so a lot of people, it is kind of like JPEG compression, but I don't think it's quite the same. I don't remember what JPEG does, but I'd be surprised if they use an octree underneath for JPEG compression. But actually, let's see. I might be completely wrong about that. So color quantization. I could be wrong. So use color quantization. Let's see. History and applications. So in the early days of PCs, it was common for video adapters to support only 2, 4, 16, or eventually 256 colors due to video memory limitations. Right. So this is something that they'd use in GIFs. So nowadays, color quantization's mainly used in GIF and PNG images. GIF, for the longest time, for a long time, the most popular lossless and animated bitmap format of the World Wide Web, only supports up to 256 colors. So I knew it was used in graphics interchange format files, but I didn't know it was used in PNG. That is surprising. PNG images support 24-bit color, but can often be made much smaller in file size without much visual degradation by applying a color quantization, since PNG files use fewer bits per pixel for palletized images. Interesting. Okay, well, yeah, so that's stuff to know. So this particular variant of color quantization, I don't even know if it's available here. So the most standard techniques treat color quantization as a problem of clustering points in 3-dimensional space, where the points represent colors found in the original image, and the 3 axes represent the 3 color channels. Almost any 3-dimensional clustering algorithm can be applied to color quantization and vice versa. After the clusters are located, typically the points in each cluster are averaged to obtain representative colors that all colors in the cluster are mapped to. The 3 color channels are usually red, green, and blue, but other popular choice is the lab color space, which in which Euclidean distance is more consistent with perceptual distance. Yeah, so maybe just to start, just because we want to kind of get something working for now, the first thing I'm going to do, because I think it's easy, is use Hsv instead of RGB. Now I think Hsv, what's the difference between Hsv and Hsl? Should we actually be using Hsl? Well, what is actually? I need to think about that. Hsv, Hsv versus Hsl. So let's see. Hsv and Hsl are also known as Hsb, are alternative representations of the RGB color model designed in the 1970s by computer graphics researchers to more closely align with the way human vision perceives color making attributes. And these models, yeah, okay. So let's try Hsv and let's see if the images change any when we use Hsv. That's the first thing we'll try. Because that's an easy to do. And honestly, I've been streaming for about 4 or 5 hours now, something like that. So I'm kind of teetering out on the my utility here. I know a lot of people can go like all day, but I don't have that amount of stream stamina, so I cannot. Also, I just got a notification from work that I have to check over here. Oh no. How did I get 5 notifications? Okay, I'll have to check that in a bit. So, okay, so that limits the amount of time that I have left for stream because I have to actually answer that one to maybe another 20 or 30 minutes or so. I'm really sorry about that, guys. But I do actually have to answer those. And they're people that live in Japan, so and now's the best time if I'm actually going to talk to them. So, let's go and do that. So, let's do the Hsv color space first. So, what we're going to do is we're going to modify all of these guys to Hsv. So, any RGB we're going to modify to Hsv. And let me see if we can just convert the image to Hsv. So we have an image, which is RGB. Can I just do Hsv of image? Does this do anything? Hsv dot of image? It seems like it converts to Hsv just fine. So let's commit what we have. So git commit, git status, dot, git, let's do vi.git ignore, and we're going to do star.toml, star.png, star.jpg. I think that's what I need. Is there any other image format that we might have? I think that's fine. Oh, and also star.mp4. All right. Git status, git add.git ignore, and git add source quantize. .jl. Git commit -m. Are you working straight from command line? Yeah, I am. Git commit m, and what are we going to do here? We're going to say adding working draft for color quantization. All right, git push, origin development. All right, also Awkward Island, thank you so much for following, really appreciate it. Okay, so now let's open up the last VI, change it to Hsv. I wanted to make sure that we had, something that was available. Just the same thing again. 1 second. I just want to make sure I had something like online just in case I break everything, right? So let's go to the RGBs here and let's change this to Hsv. Thank you for streaming. Yeah, thanks for being here. So where's the next RGB? Box color is now again going to be Hsv of 0. And the color set is going to be Hsv of 0. Oh. Well, okay. Well, if that's all we have to do, let's say image is going to be equal to, again, the pride flag is what we're going to load here. Oh, crap, something broke. What broke? Failed to revise, quantize, let me just try quitting Julia and open it up again using revise. And now we're going to do using Quiltify. And see if it breaks. It probably will. Seagull Rush, thank you again for following. Really appreciate it. Okay, give it a second to precompile. It's precompiling the image and image view libraries, which sometimes take a while. But cool, I'm actually really happy with this image we have up here in the corner. Like, it's nice. It's been a while since we did color quantization, and I realize the way that we're doing color quantization isn't the typical way in which people do color quantization. Again, using a KD tree is probably a bit better, but here we're literally just doing an awk tree. Do they use a KD tree in JPEG? They actually might. You might be right about that. So we're going to say, I need to think. We're going to do using image and image view. All right. And now let's do img is going to be equal to pride.jpg. And now I want to just do img2 is going to be equal to quiltify quantize 9. That should be correct. Error automatic conversion from Float64 to Hsv. Interesting. So I can't just do Hsv of 0. What does that do? 0.0. How do I create an Hsv image? So I know I can do RGB of 0, and that'll work. So can I just, do I need to do Hsv of RGB of 0? Maybe. I don't really like doing that, but it'll work. Of RGB 0, and then we can see what it looks like. So let's try that again. Let me choose Quiltify, Quantize, see what we got. No automatic conversion from Float64 to Hsv. So this is going to be on line 112. On line 464, that's not right. 40. Box by colors Hsv. I guess we have to do Hsv of RGB of 0. I don't really like the way that works, so let's see. No method matching plus of Hsv float 64. Oh no, you can't add Hsv values? So we have to add everything in RGB and then convert to Hsv? This is going to be a bit more of a pain than I thought. So the issue here, just in case anyone's not following, is we have an RGB color, right? Which is red, green, blue. And we want to convert that to a lab format, which basically means that essentially we can look at the colors and they more closely resemble the difference between two colors in Hsv more closely resembles what you visually expect the difference between those two colors to be. Meanwhile, for RGB, that's not typically the case. Like you typically, if you just see an RGB image, you tend to over rely on the red or something like that. I think it's like 0.66 on red, and then 0.3 or something on blue, and 0.1 on green or something like this. So because you over rely on the red, it's not really a consistent color space because you end up focusing too much on one color, right? So because of that, you want to move to Hsv, where you don't focus as much on any one color. But for some reason, the libraries don't allow me to use Hsv appropriately. That is to say, I don't fully understand how to like add two Hsv elements, for example. Whereas I do know how to do that with RGB. You just add them together. So, but maybe the issue here is just with, I'm adding an Hsv to an RGB, and that's because each pixel, okay, so maybe the issue here is that I just need to change this to Hsv as well. And the inbox command also needs to change. So we're going to say if pixel of R, so we're going to say pixel is going to be equal to, we'll say, I'm going to call it temp pixel. Is going to be equal to pixel Hsv of pixel. All right, and then down here we're just going to say temp pixel. There, 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 and then here, there, and there. Write that. Let's see what happens. Temp pixel not defined. That is because I called it RMP pixel. Try that one again. Has no field R. Hsv. Oh, that's because it's going to be HS and V. So let's do Hsv of RGB of 0. And now we're going to do C is going to be equal to that. I should be able to C.H. Yeah. So HSV. And we're going to do Hsv again down here. HSV. Okay. Write that. Thanks, Bashuleos, for telling me to get back to work. And now we'll do image 2. No method matching plus of Hsv float 64 and Hsv float 32. Also, in the image that we're loading, it's apparently all already, like, we're already getting nothings here, which is not good. That basically means that as we're quantizing the image, there's nothing in that box. So I know this is kind of lame, but I think I'm gonna punt on this one. I'm gonna get back to this one a bit later. Let's return it to RGB because I'm kind of iffy on this, and I'm not sure exactly what we need to do to get this to fix this, because we can't even add two float 64 elements. I think the truth is that Hsv is not super well supported in the images library for Julia, and because of that, I'm kind of iffy on whether we should support it either. Besides, most color quantization I think does it in RGB space anyway. Mostly SMW. Thank you so much for following. Really appreciate it. So yeah, let's just go back to what we had a second ago. Git checkout, source, and then quantize .jl. I misspelled checkout. Try that one again. Okay, so go to vi source and quantize. I still want to get at least one of these to-dos done. So quantization may fail. All colors are in the same color set. Oh no, that has already been fixed. So that's been fixed. Take the n most populated boxes, and let's go down here. We've got divide octree, find color set. We could pretty easily turn this into a breadth first search instead of a depth first search, I think. That is one that we could knock out pretty quickly. I think this should inform JPEG compression. Right. Oh yeah, DCT. Yeah, I know DCT. Oh wait, it's literally just a DCT? No, it can't be just a DCT. There's no way it's just a DCT. It has to be the DCT on top of stuff, right? It's used most often. I mean, I know you can use it for JPEG. Let's look for cosine. Let's see. The basis for JPEG is the discrete cosine transform, a lossy image compression technique that was first proposed by Nasir Ahmed. People use the DCT for a compression method? I guess that's fair. No, that's fair. So for those of you guys who don't know what the DCT is, but you know what the FFT is, the DCT is the real part of the fast Fourier transform. I did not realize that it's literally just taking the discrete cosine transform and removing probably the unnecessary part. So probably what happens is the following. So let me go over here. I'm just guessing. I have no idea, but this makes sense. Drill new page before. Let's say you have an image, right? The image is, here's your image, and it's like super messy. You've got a whole bunch of lines, all this stuff over here, right? Well, okay. You can turn this into another space where essentially in this space, all this mess goes away and you see essentially just this kind of like star in the center, right? Right. So this means if you move this into another space where there's much less data available in the space, you can kind of remove all this stuff outside and just keep the data in the center, right? So as a compression technique, that makes sense. It means you lose some information. Like, for example, this is not just like a star in the center. It actually is like a gradient that moves this direction, right? So you're technically removing information, but most of the information is, like 90% of the information is within this bubble in here. That was 9%. Let's try drawing 90%. Try that again. So 90% is within this bubble over here. So the idea is you just move to another space, you keep what's in the bubble, and you remove that 10% of information that no one's actually looking at anyway. We actually did a challenge not too long ago where I was trying to draw in this space over here and then convert it over into this space. We didn't get very far, but we did create an interferometer, so that was interesting. I need to go back to that, actually. That was quite interesting. I've been wanting to do more programming challenges, but again, I just don't know how to put that onto YouTube or Twitch. Or I don't know how to put that onto YouTube. It makes for like interesting Twitch content, but even then, my Twitch viewership on those streams usually end up being like lower than my Twitch viewership on like normal streams. So I feel like there isn't really any incentive for me to do it, you know? Anyway, let's keep going. So this to-do of using the breadth first search instead of the depth first search, the idea here is that, again, we've got some sort of set of color boxes. So here's our color boxes. And we're currently doing the depth first search, which means we go all the way down here, and then we pick the colors from the bottom up. But in actuality, more than likely, these boxes are going to be more filled than the boxes underneath them. So for that reason, we want to do a breadth first search instead of a depth first search. So let's just go ahead and knock that out. Luckily, there is a website online called the Algorithm Archive, which already has tree traversal inside of it for Julia. So I think we can just do, yeah, so I think we'll just go ahead and take a look at how we did the stack and everything in here. Breadth first search queue. Yeah, here. So literally we just have to use data structures, have the queue associated with it, and then we should just be able to modify this. So let's go here. And let's paste this code, and then we'll modify that code. And also, I think at the top here, I need to do using data structures. Okay, so let's do BFS. Okay, so the way this works is so here's where we're doing the recursion. So down here, probably what we want to do is we want to say for child in box.children. So for child in temp.children, we enqueue. So up here, I think all I need to do is say we have a queue. Oh, actually, probably want to do this after the return. So box.color is set to nothing. Yeah, so in here, we want to go ahead and initialize the queue. So we're going to say queue is going to be equal to queue of, what did I call the node? Color box. Color box. I think I need to give it an initial element. So let's see. So, oh no, I think I can just use this. Yep, that'll work. Okay. So then we just enqueue onto the color box, the box that we're on. So we'll do enqueue onto queue, and then we're going to put the box. So it should just be box. Okay. So now down here, we're going to say while length of queue is greater than 0. Yep. While length of queue is greater than 0. That'll do. End there. And now we're just going to say for child. In child, we're just going to enqueue. Enqueue. This is really annoying. I'm sorry about this. Queue. And then we're going to do child. Yep, child. That'll do. And down here we have to end. Okay, so while length of queue is greater than queue, we're then going to do the information, which is going to be find color set on color set child here. So on whatever element we're on. So we're going to say temp. It's going to be equal to d q u e u e u e q. So we're going to take that element here, and then we're going to say find color set for child in temp.children. Okay, so this should be right. So the idea here, again, for a breadth first search, in case you guys haven't been aware, did I say thanks for following mostly SMW? I do appreciate the follow. Sorry if I missed that a few minutes ago. The idea here is that we basically create a queue, we put the initial element inside of it, we pop that queue to create this temporary value here. We find the color set on that temporary element. So find color set should be on child. It should be on temp. Okay. Wait a minute. I think I need to think about this a little bit more, because finding color set on temp. We've already done. Okay, I see what I need to do. What I need to do is say, okay, so now we're not doing this in a recursive fashion. Okay, I understand. And while I need to think about this. Index is less than the total number of colors. Sure. Okay. And then I just need to take these guys, yank for yank, and paste it down here. Oh, hello there. Okay. Find color set is no longer used there. And then we should just enqueue the children. Return question, but what font are you using? So actually, I'm using a bitmap font available in Xterm. It's just the default Xterm font. If I'm being honest, the reason I'm using Xterm is because I really like Xterm fonts. I love bitmap fonts. In addition, you can do some cool stuff with Xterm. So let's CD into pictures, ls, CD into stream maybe, ls here. Oh yeah, so I can just do, let me make this huge really quick. So I can do this thing with Hsl. So I can do, if I do img to Hsl, and then I do hair.png. Oh, hair1.png. Okay, so that's one of my emotes. But the point is, you can like directly show these images in the terminal, which is really cool. So like scow.png. .png. Here's my spherical cow logo. So there's a lot of cool stuff that you can do with Xterm that I quite like. So I think I can delete these here. Okay, and let me make sure I've done this right. So we say we have a queue. We enqueue the queue with a big box at the top. Then we say while the length of the queue is greater than 0, meaning we have an element in the queue, and the index is less than the color num. So here we're going to set some sort of index. It's going to be equal to 0, I guess. We'll set it to 1. Then in here we're going to say index plus equals 1. And then down here we're going to make it so we no longer need the index to be read in, but we do still need the color num to be read in. Okay, so we have the index is equal to 1. And then basically, yeah, we just keep going. Yeah, okay, this should do. So now where is our find color set? Should be down here. And now I can just remove this here, write that, and does this work? It does not. Dang it. Julia is one-based indexing, unfortunately. So let's try Julia using revise, and now let's do using Quiltify, and go from there. String question. Oh, okay. I'm gonna have to check Xterm out. Yeah, so it's specifically a Linux terminal. Oh, you know, maybe. Okay, well, let's just see what it says. It's probably gonna break somewhere. Undefined node not defined. Correct. Where did I use the term node? Oh, it must be up here. So I just need to remove this guy. Okay, write that, go over here, try it again. And then in principle, this should build. And then we can just try color quantization with breadth first search instead of depth first search. Again, it's just better for this application. That doesn't mean it's best for all applications. Okay, so I do have to make sure that I add data structures to the dependencies here. You have index array usage. You have index as array usage. Oh, correct. Thank you so much. That was, so the reason I did that before was because, well, we were doing a depth first search, which means you don't really know where you are on the tree because you're using recursion, right? And so because of that, I had to use a pointer instead of using a, structures, instead of doing just an element. First line of the function also, thank you. But also, I don't think we need this anymore. I think we can delete that now that we're using a queue. So. All right, appreciate that. Thank you so much for that. Okay, so let's go here, and now we're just going to do using images, and then image view. All right, should be pretty quick, unless I'm dumb. Well, okay, I guess I'm dumb. Give me just a second. Okay, so now we're going to load an image. Image is going to equal to load pride, and now we should be able to do image 2 is going to be equal to quiltify quantize 9. Does this work? It looks like it's working. DQ not defined because I'm dumb. DQUE. UE. Try it again. Okay, so this is working. Okay, so now let's take a look at image 2. Image show img2. Hopefully it looks nice. It should be a quantized version of the pride flag. And okay, yeah, okay, that's not quite what I wanted. That is significantly worse than the depth first search version of it. And this is because if box.color, this should be temp.color. And this should also be temp.color. Try it again. Nope. Try it again. Yeah, because, okay, so now we're going to try imshow. Okay, there we go. That's kind of what I was looking for. Again, it's a bit weird that this color is gray instead of white. We are getting 9 elements. So that is one difference that I'm not. Oh, probably less than or equal to color num is the reason. Try that again. So let's do quiltify, quantize, and then hopefully image 2. Okay, there we go. That's the image I wanted. Perfect. It is exactly the same image we had before. It's just now we're using, again, breadth first search, which will be slightly more efficient for this particular iteration scheme. Unfortunately, the data structure that we're using here is a bit slow. Queues are just slow in Julia. That isn't great, but also it'll work. And unfortunately, I have to go to answer some stuff for work. So I'm just gonna go ahead and do git add source quantize. And if there's anybody that you want me to raid at the end of stream, feel free to let me know, and I'll totally try to raid them if they're doing like programming and tech content. Otherwise, I'll go ahead and select from my list of people. So let's do git commit -m, changing DFS to BFS. All right, git push, origin, and then we want to go to development. Okay, great. So again, if there's anybody that you want me to raid, feel free to let me know. We could do, let's see, who do we have? We've got Strager doing science and technology content. Kit Boga's rerunning. Master Mindo is a wonderful streamer. If you guys haven't checked them out already, they're great. In fact, let's do Master Mindo. I quite like their stream. They're really cool. So let's do raid on Master MNDIO. Okay, that is it for today. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. I'll be live tomorrow, hopefully at 3:00 p.m. is what I'm hoping for, and I'll do 3 hours of MIT stuff, working on both the MIT coursework for my lecture and also Klima, and then I'll also focus on Quiltify tomorrow evening as well. So hopefully I'll be able to catch you there. Have a wonderful time until then, and yeah, I'll see you next time. Bye, guys.